All right. So let's begin. Any questions from last time? Okay, so we want to continue our discussion of the early thermal history of the universe. We're going to start back at the really highest temperatures, and that will mean, for our purposes, temperatures higher than the top mass, the heaviest particle in the standard model, and then we'll see what happens as we start lowering the temperature from that point. And then until essentially all the particles have become non-relativistic, except of course the photon, and for our discussion here, the neutrinos. All right, so just a recap from last time. If you're at a temperature much bigger than the mass of the particle, the number density of a species I is just the number of degrees of freedom, some zeta function, zeta factor, pi squared t cubed for bosons, and then there's some 3/4 for fermions. Okay, and relatedly, the energy density we also computed like this, and it goes like T to the 4 for bosons, and then there's a 7/8 for fermions. And useful to remember, these prefactors here are not terribly far from 1. So it's useful to remember that the number densities are just order T cubed, whether you're talking about a boson or a fermion, and the energy densities are order T to the 4. Okay. So if we look at the total now, and we can talk about the total energy density. Okay, we don't directly talk about the total number density per se, although there'll be a related issue when later today we talk about entropy. But total energy density, of course, is very important because it feeds into the Friedmann equation. And the total we write, as we said at the end of last time, we just want to sum these formulas here. And the G at the front we call G star, pi squared over 30 T to the 4, where G star is a sum of, all right, B, not for baryon at this point, B for bosons. Is that okay? Sometimes I use B for baryon, but here I mean B for boson. And then the 7/8 for fermions. Okay, and one other thing we discussed last time is that the baryon to photon ratio, so then this is going to be B for baryon, eta, which is the number of baryons minus the number of antibaryons over the number of photons, is about 6 by 10 to the minus 10. Right, so we said for every baryon, there's about 1 billion or so photons. But let's also just make it clear that why this is so important. If we go back to really early times, where these things become relativistic, even the baryons, the protons and so on become relativistic, these formulas here tell us that if you're in the relativistic regime, so this is also a relativistic regime, the number densities of these things are all comparable. Like the number density of photons, as we said last time, was similar to the number density of some relativistic species. Okay, there's some 3/4 factor, but they're comparable. Remember? Okay. So therefore, at T much bigger, say, than the mass of a baryon, N gamma is order the number density of the baryon itself, right? Up to some 3/4 factor. Okay. So if you look at this eta here, that means this thing here, eta, is order n baryon minus the number of antibaryons over the number of baryons at these high temperatures, not at low temperatures, right? The denominator I can estimate is number of baryons or antibaryons, okay? And if you go back, and there are baryon preserving processes, the difference between number of baryons and antibaryons won't change, right? If we don't have baryon violating processes. So therefore, this number will remain, you know, there's some 3/4 whatever, so let's just say order 10 to the minus 9. Okay, so that's why it's a precise thing to say that in the early universe, for every billion antibaryons, there was 1,000,000,001 baryons, roughly. Okay, even though that's not true today, of course. All right. So let's now, questions about this? So let's now compute this G star at these really high temperatures, and then we'll lower the temperature. Okay, so let's consider temperatures higher than the top mass. And I picked that, okay, 170 GeV. Heaviest particle in standard model. Okay, so then all the particles are relativistic, and we can use these formulas for every particle in the standard model. By the way, just to put this in some perspective, right, because not everyone maybe is used to talking about temperatures in GeV. Let's just emphasize the point once again. So also always remember, so a Kelvin is about 10 to the minus 4 EV. Okay. So if you're talking, let's call this order 100 GeV. Okay. So that's 10 to the 11 EV. So you're up by a factor of 10 to the 15. So 10 to the 15 Kelvin is on the order of 100 GeV. Okay. So we're talking temperatures above this. Okay. So this is hot stuff, 10 to the 15 Kelvin. Okay. So by the way, to your question about last time, amino acids for sure will have destroyed at these crazy temperatures. That's right. Yeah, good. Yes, everything we're going to say is within the first second. And the connection between the temperature and the time will flesh out explicitly later. That's right. Yeah, it's basically the first second, everything we're going to say. All right. So let's compute this G star at these high temperatures. So this is just a bit of counting. So all we do is count all the particles in the standard model. All right, so let's start with the bosons. All right, so maybe someone can tell me, what do we have here? What should I write? We name some bosons in the standard model, one at a time. Say it again. No, what are the particle names before we specify the number? Everything. Everything's a boson. That's a little too strong, yeah. Photons, okay, so for photons, for sure, we'll put a 2. Okay, then what else do we have? Sorry, W plus minus. That's right. And for each W, what should we put? A 2 or a 2? Well, yes and no. So it's in some sense, yes, if we're at such high temperatures that we restore electroweak symmetry, or we can remember that the W wants to pick up a mass, so it has 3. But these ways of counting are all equivalent. Okay, so we can do this for W plus, W minus, and the Z. And then what else do we have? Gluons. And what G should I put for the gluons? 16, very good. Yep, so there's 8 gluons and they each have 2 spins. And then what other boson do we have? Yep, Higgs. Okay, and the way I've done the counting, I'm only going to put 1 for the Higgs. Okay, so, or equivalently, we could have written 2, 2, 2 here, and then 4 for the Higgs. We can go back and forth. All right, so that takes care of the bosons. And now, well, maybe I'll put it up above because I ran out of room. The 7/8 for the fermions. Okay, so for fermions, let's start with maybe the charged leptons. Okay, so I'll put a 4 here if that's okay. So by that I mean the electron, 2 spins of the electron as well as the positron. So I'm going to list that as 4. Okay, so I'll put E plus E minus together. And then we'll multiply by 3 for the 3 generations of leptons. Okay, so let's just call this charged leptons. All right, and then for quarks, what should I put? So we'll start with the 4. Okay, take care of the 2 spins of a quark as well as the antiquark. So 4 times what? A 16. I don't know if we need, not necessarily 16. So we should start. How many quarks are there? Types of quarks. So how many flavors of quarks? 3? 6. Yeah, up, down, strange, charm, top, bottom. So we got to put a 6 here. And then there was another factor we mentioned last time. 3 for color. Yeah, so we have all this. So these are the quarks. And then we need to add the neutrinos. And for the neutrinos, we have to be a little careful. I shouldn't just write 4 times 3. Instead, I'm going to write 2 times 3. The 3 for the 3 generations. And then the 2, because we only have one type of neutrino. There's the left-handed neutrino and the right-handed antineutrino, and that's it. Okay, in the standard model. So that's why I put a 2 there. All right, so I think that's everything. And then you add all this up, and you get 106.75. All right. So you could say that's kind of the number of degrees of freedom of the standard model, sort of, but there's a 7/8 there, but okay. So that's the prefactor we put in this formula, and then we specify the energy density at these high temperatures. Yes? Well, let's bear in mind that's a different G. That's to do with the magnetic moment of the muon. And yeah, so we're not going to get into that level of precision, let's say. Any other questions about this? Well, no, I think if they're Majorana and they have a mass coming from seesaw, then I would say this is correct because the other one is thought to be very heavy. But we don't know. So yeah, if the other one has a really, even a super heavy mass, this is a good estimate. The other thing is if they were Dirac, you should put a 4 here. Then you should, I thought you were going to ask me if they're Dirac, because then you have the left and right and they're both light. But in that case, it's a bit of a long story, but the right-handed guy, as you know, would couple so weakly, it may not be in thermal equilibrium with this other stuff. Yeah. So this estimate is probably right. And even the left-handed neutrinos that we're including are going to decouple in this story, which we're going to come to later on. But yeah, we could have other stuff that's even less coupled to the standard model than this, and they will contribute even less to these sums. Okay, good. Well, yeah, so I'm happy to include the graviton. And that, if we take the rules at face value, we should include that. But similarly, we would have to go to extremely high temperatures for the graviton to be in thermal equilibrium, up towards the Planck mass. So below that, the graviton decouples and will provide, again, a small contribution to this. So when things decouple, their effective temperature turns out to be less than the T here. This T is, we can always think of T as the T of the photon. And at the moment, this is the T of everything else. And when things decouple, they'll end up with a lower temperature for reasons we're going to come to. I haven't explained that yet. But yeah, so the graviton would be expected to be at a somewhat lower temperature than these other species today. And then when you raise the T to the 4 small number, it ends up contributing quite small contribution. I'm not saying that's obvious, but we can talk about a related issue with the neutrinos. All right. So now I want to talk about what happens when the temperature drops below the mass of some particle of interest. Okay, whatever particle, the top, first of all, but then all the other particles, we can just keep on going one by one. So at some point we should worry what happens when it drops below the proton mass, what happens when it drops below the electron mass, and so on. Okay, so let's just go back to our formula for the number density for some species I. Oops. Now I'm going to write the energy EP plus or minus 1. We'll do bosons and fermions all together. And in this regime, okay, this is the non-relativistic regime now. EP is approximately m, right? It's root p squared plus m squared. And now it's approximately m plus p squared over 2m. Okay. At low temperatures, you're dominated by the lowest values of E that are available. So the lowest momenta will dominate the integral. So that's why I write that. Okay, so if I plug that in here, you see this has some big e to the m over t, and then an e to the, this should be, oh, that's right, p squared over 2mt plus or minus 1. Okay, so this e to the m over t is critical, right? Because we're at low temperatures, that's what we're doing. So e to the m over t is a gigantic number, okay? E to the m over t, let's say, is much, 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 much bigger than 1. Right? You go down to, say, 0.1 the mass, 0.01 the mass, et cetera, you're getting e to the 10, e to the 100, so on and so forth. So this is a gigantic number as we get to lower temperatures. And that means that this term here, first of all, completely dominates over the plus minus 1. The plus minus 1 in this limit is completely irrelevant compared to some exponentially large quantity. And so in this way, you can ignore this. And in this way, the bosons and the fermions will share the same approximation. Okay, so this becomes GI. I ignore that. So I can just move this upstairs. I can pull out the e to the minus m over t. That's a constant for the integral. And then what you have left is a nice little Gaussian integral. Is that okay? So it's exponentially small because of the e to the minus m over t and some Gaussian. Okay, and then you could just do the Gaussian and you'll get like this, m, t. I don't know, I could put an I here maybe. I should say the mass of the ith species, if you like. Okay. Anyway, 2 pi, 3 halves. So there's the number density. And the energy density, we don't have to redo anything, really. It's the energy density for non-relativistic particles is just the mass of the particle times its number density. It's nothing fancy when they're non-relativistic. So I just multiply this by a factor of m. Okay, I can write that out, I guess. Okay, so both the number density and the energy density are exponentially small quantities as we go to low temperatures. So let's have a little plot of this, what's going on. So let's plot the number. So the number of a species is just the number density times the volume. So you just pick some volume of interest. Volume is going to expand with the universe. Volume is proportional to a cubed. And remember we said temperature goes like 1 over the scale factor. So this is also proportional to 1 over t cubed. Okay. So if you plot the number of some species, as long as it remains relativistic, right, first of all, at high temperatures, so I'm going to put on this axis here 1 over t. So this is like time is going that way. Okay, so down here at 0, this is as t goes to infinity. This is the high temperature early universe. We're in the relativistic regime initially. Number density goes like temperature cubed, as we said. Right, down here, n is like t cubed. But the volume is dropping like 1 over t cubed. So therefore, for a while, this just stays constant. So it looks like that. And if these are just photons, let's say, it will just persist like that. There'll be a subtlety that we'll discuss later, but it more or less stays constant. Okay, this is just saying that over here you have some box of particles. Okay. And you filled it with these little particles. And then the universe expands. But if you had, 1,000 particles in the box and the universe expands, you still have like 1,000 particles in the box, and the number stays put. It's not very deep. All right, but then we're saying if we're dealing with massive particles, there's a point here, which is 1 over the mass of the particle, where things change dramatically. Once you get to temperatures below that, the numbers are dropping exponentially. Okay, so for some other species, let's say in red, so let's say this was the photon. For some other species, let's say this is, I don't know, E plus, E minus, or let's say electrons, okay? So I'll draw the electrons almost the same as the photon. There was some 3/4 difference, if you remember, okay? But it's almost the same thing. So it's going to go along merrily like this. And then when we go past the mass, there's some radical drop in the behavior, exponentially falling. That's what these formulas predict. So it just somehow keeps on going down. So there's some e to the minus mt factor. And it's sometimes called Boltzmann suppression. So if I were to if I add the electrons to this box, or electrons and positrons, in the high temperature regime, right, there's a bunch of E pluses and some E minuses. But then over in this regime over here, the E pluses and E minuses are basically annihilated away. That's what this is saying. Okay? So the physical process is that they've gone, and you're just left with a bunch of photons or other stuff. But the E plus, E minus is gone. Okay? And there'll be a slight wrinkle in the behavior of the photons as we go forward, but almost constant. Oh, well, I just erased the baryon to photon ratio, but let's just remember, if you took this formula literally, you would say as I go to lower and lower temperatures, I just get this insane exponential suppression. This thing is basically zero today, right? Because today's temperature of the CMB is 10 to the minus 4 eV. So you have, e to the minus a million or something. This is zero, okay? So it cannot be that this formula is literally true forever and ever. And it won't be true forever and ever because there's that baryon, anti-baryon, or electron, anti-electron asymmetry at 1 part in a billion, right? So in this regime, they keep annihilating, and then there's just the extra, 1 out of a billion electrons left over that didn't annihilate. So really, there's just occasional electron left over, for example, or baryon. And so really, this picture is that it goes down, 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 and then eventually flattens out with the tiny asymmetry left. Okay, and this ratio here, what we're saying, this is on the order of 10 to the 9, this drop in the number. So think of these on a log scale. So the picture, at least in this regime here, as we're plummeting, there's exponential dropping. Now, E plus E minus annihilation processes are somehow happening, right? You're still in thermal equilibrium. I'm still attaching the same temperature T to the electron, the positron, as the photon. And in equilibrium, these processes are happening forwards and backwards in time, I should emphasize. Okay, so in this regime here, it's telling us that on the one hand, the formulas say the number density of E plus E minus is very small. Okay, so when an E plus and an E minus get near one another, they're happy to annihilate. But they don't get near one another very often because they have such a low density down here. So they only occasionally meet one another and produce a pair of photons. Okay, so that's happening in this direction. So this direction you can see is a slow rate because there aren't many E plus E minus around. If they're happy to annihilate, but there's so few. There's one there and there's one over there, and there aren't many of them. So that's why the rate this way is small. On the other hand, the rate this way in equilibrium has to be the same. That's what thermal equilibrium tells you. And the direction that way from 2 photons into E plus E minus, it seems unusual that that would be small because there's still a huge number of photons around. The photons have not disappeared. So who can tell me if there's a huge number of photons around, why don't they just annihilate into E plus E minus at a fast rate rather than the slow rate? Yeah. Well, your hot is the right word, but
they have charge. So if you're like back in the early universe and like these things are happening, maybe they're just getting scattered instead of just like.
Well, the fact that they have charge is not directly, I mean, the charge allows for this process to occur, but other than that, we don't have to pay too much attention to it.
Say that backwards doesn't necessarily happen. I mean, they don't annihilate and like, oh.
Yeah, but why don't they annihilate rapidly?
They have a lot of energy.
The photons? Oh, but okay, but are you saying the photons have a lot of energy or little energy?
Like.
Okay, okay, well, let's think. We're now dropping to temperatures below the mass of the electron. So do the photons have a lot of energy? What's the typical energy of a photon? Average energy of a photon is what? How can we estimate that in terms of temperature? 2.7, whatever, 2.7 times the temperature. So order T. Okay, so when you're down here, the photons have a huge number, but each photon doesn't have much energy. Well, they have a distribution. Okay, so here's the distribution of photons. Here's the energy. And the peak is around T or so. So up here, you have some distribution that looks like this. Okay, so let's say in region 1, let's say that's the picture. And the electron, oh, yeah, let's say, give me some more room here. So initially, we're at high temperatures. That's the photon distribution. And high meaning the mass of the electron is, say, here somewhere. And so there's a huge number of photons available that have enough energy to pair create. So that's back here. And so the forwards and backwards process happens easily. Both electrons, positrons, photons all have a lot of energy. They're happily going back and forth. But then this is scenario 1, high temperature. And then if this is scenario 2, the low temperature regime, the whole distribution is moved to the left. So now it's low temperature, looks something like this. Low temperatures. Okay, the electron mass hasn't moved, of course. So now the photons, well, there's still a large number of them. Very rarely do the photons have enough energy to pair produce electrons and positrons. So it's only in the tail of the distribution that that's possible. So it becomes exponentially rare, and you see it's connected to this exponential suppression. Okay. So yeah, so they maintain equilibrium, but the reasons the rates match has kind of different reasons, but they do match. So any questions about this? Okay, so every time you go past, let's say, a mass threshold and temperature drops below the mass of some particle, there's a pretty rapid transition from number densities being important, like T cubed, to just exponentially falling and being almost irrelevant in terms of the total density or even the total energy density, right? Because the energy density also is e to the minus m over t. So that means when we compute this G star, the moment we drop below some masses, we have to immediately start reducing this number. Okay, we can kind of eliminate it from our counting. Does that make sense? We could put in a G star of, 2 for the electron, but we should then multiply it by some exponentially small quantity. So we might as well just delete that to a first approximation. Is that all right? Okay, so let's try and get a rough idea as to how this G star actually evolves in time. So what I want to say is roughly, well, pretty accurately actually, let's say the contribution to this G star, right? Remember, G star is just the prefactor we're putting in front of our expression for the energy density, is the species degrees of freedom, Gi, at temperatures much bigger than the mass of the particle, and then approximately more or less 0 at temperatures much less than the mass, right? I should really write an exponentially small quantity here, but that's so close to 0, might as well put 0. Is that all right? Okay. So let's try to plot G star, which again, is therefore effectively controlling the expansion rate of the universe, apart from the temperature. Was there a question? Sorry. And let's plot this one. I need a bit more room. Okay, so again, this is 1 over temperature, and this will be related to time, going to the right. And we're going to plot G star. Okay, so initially, we already said we're at 106.75 from all the degrees of freedom of the standard model. And that will first drop once you go below the top mass. And we have to delete the contribution from the top mass to our sum that we wrote a minute ago. But let's just put in here, say, 100 GeV. Okay, as a reference value. And we're going to think of this as a log scale. So anything within an order of magnitude of 100 has a mass order 100 GeV, let's say, we're quickly going to drop below the masses of all those particles. So that will be the top, the Higgs, the W, and the Z. Okay, so basically in a regime that's pretty close to order 100 GeV, we're going to drop. And then it will flatten again. So here we have all standard model. And around 100 GeV, it's going to be all minus top W Z Higgs. Okay, just subtract those 4 type of particles from our summation. Does that make sense? Okay, so let's say you get down to, yeah, here. So I don't know, 50 GeV or so. These ones are all exponentially suppressed. Okay, if you just subtract out the 3s from the W's and the Z's and whatever from the top, this number comes out to be can check that this number is 86.75. Okay, that's if you remove those particles from the sum. And then we can keep going, and I don't want to be too precise about this, worrying about every mass of every particle, but roughly speaking, at around a GeV, somewhere in the order of magnitude of a GeV, there are many other particle masses. Okay, so even the bottom quark is near, a few GeV, and so forth. Okay, and the QCD phase transition and so on is all happening here. So at this point, there are going to be many species that we have to drop from the sum. And this G star is going to plummet yet again. Okay, and so now I'm going to tell you not what to subtract, but the only stuff that I'm going to care about at this point, a little bit below a GeV. Okay, say 0.1 GeV and below. We're going to keep photons in the sum, E plus, E minus, neutrinos. Does that make sense? So down here, right, even the protons and everything are all exponentially suppressed. And these ones are the ones left over. And then there'll be another important era here, which is about an MeV, which is around the mass of the electron. So on this side, the electrons and positrons are annihilating, and on this side, they're still relativistic. Okay, so maybe this number is kind of important. Let's directly compute the G star of those things. Let's see if we can do that. So, yeah, so below GeV, G star is something like 2 from the photon. And then the rest are fermions, so I put a 7/8. The electrons and positrons is 4, right? 2 for spin, and then particle, any particle. And then the neutrinos, which we said is 2 times 3 for the 3 flavors of neutrinos. So this number is 10.75. Let's just remember that. So here I'm going to write 10.75. Any questions about this picture? Yeah. Yeah.
Talk about what's actually happening plus minuses. But I'm looking at like the data set that from think about those things. Is there a different process that I can visualize for what's happening in the or are they different
Yeah, the W pluses and W minuses will just annihilate into themselves. And the Z, well, the Z is its own antiparticle. It will annihilate into itself, so to speak. And the Higgs, yep. So the Higgs, yeah, I mean, the Higgs couples to all sorts of things, right? So let's see. Yeah, pick whatever you want. Let's say E minus, E plus, although it doesn't couple to the Higgs much, but it's example, Higgs, Higgs, so on and so forth. Yeah, the Higgs has Yukawa couplings with all the fermions, so you can draw these kinds of diagrams. So yeah, the Higgs will just disappear. All of them will disappear. Other questions? Hmm. But beyond the standard model, yeah, I mean, if they have an asymmetry. Yeah, I mean, if the dark stuff or whatever the other stuff is has uh, is symmetric between particles and antiparticles, it will be this same story. We could also have other sectors that are just completely not in equilibrium with the standard model. So they would be at a different T. But they might do this pattern, but with their own temperature, which may not be the same as the photon's temperature. So that we don't know about. Yeah, so there could be sectors that are just decoupled from us. But as we'll come to later on, as we get down to here, we're heading, so this, as you'll see, this will be about a second, and just after this is BBN. We'll have evidence that just this stuff on the board, down here at least, will be standard model. It won't be dark stuff. Okay, and so at about an MeV, so remember the electron mass is half an MeV. There's going to be another transition, which is kind of the one that I've often referred to, E plus E minus annihilation, right? E plus E minus is surviving all the way down here, but then eventually it too will disappear, and here we'll just have photons and neutrinos. Okay, below an MeV. And the value for just photons and neutrinos, if I were to write the G for that here, I would just delete that 4, that's from electrons and positrons, and keep the 2 and the neutrinos, and that's some number. And it turns out that number is not quite right for reasons that we'll discuss. But it's not a bad estimate. Okay, so we'll come back to that. All right, so any other questions about this? Okay, so let's just also draw a related picture about the energy density over time. Just one quick comment about it. Okay, so you recall early on in the course, we always were talking about rho for different types of materials versus, say, the scale factor, or kind of time going this way. And we acted like there was a clear separation between radiation, matter, and vacuum energy. Okay, so let's say this is radiation, or R for relativistic stuff, right? Which went like A to the minus 4. And then there's matter. A to the minus 3. And then dark energy or vacuum energy, which seems to be a constant. A to the 0. All right. And these crossover points, remember, this point of equality was 50,000 years. This crossover point of about 10 gigayears. And today, 13.8 gigayears. Now, what we're saying is that this picture is pretty accurate. Pretty much everything when the universe was about older than a second. And we're going to see that that MeV is about when the universe was about a second. Okay, so as long as this is older than a second, this picture is kind of fine. That's not a bad picture, therefore. But when we get back to the first second, we're having these funny transitions take place. Okay, so this isn't quite true anymore. So let's say I include the curve for, say, the protons. Okay, so the protons are a piece, right, of the matter contribution to the universe, right? About a sixth, because most of it's dark matter. So that's why I drew it a little bit below the matter curve. Okay, let's say rho proton. And so it's fine. It's just following this all the way back. But then at some super early time that we can figure out in a minute, which is back here at around a GeV or so, this is actually going to be at around a microsecond after the Big Bang. The protons were relativistic. If you go back to about less than a microsecond. So that means even the protons were up here. We should draw them up there somehow. Okay, and they're basically acting like radiation because they're relativistic. So they redshift like 1/8 to the 4. Okay, so that's what the protons were doing, right? They're order 1 up to some 3/4 whatever factor related to photons. So they're up there, hugging the photons, and yet they're down here below a microsecond when t is bigger than a microsecond because their densities plummet exponentially as they annihilate with antiprotons. And so these two curves, which you can see have a big separation, that's what that exponential fall off is doing, okay, that we drew a second ago. So I linked these by an exponentially falling quantity function. Okay, and so this height here, this is the 10 to the 9. Okay, so proton densities go on a ride that looks like that, etc. And similar for electrons, positrons, whatever. Well, for electrons. Right, so any other questions about this? Yeah, so this happens to be something like a microsecond. All right, so that's a kind of more detailed picture of what's going on. Let's convert to time to tell you why I claim it's a microsecond, if that's right. Okay, let's do this conversion now to time. Okay, anyone have an idea how I can convert this all to time? What should I do? Flip? No, reverse. Yeah, but what formula should I use to connect this to the time at which these events are taking place? Yeah, Friedman. All right, so let's use. Okay, so we'll write h, and I'm going to put a square root, right? So 8 pi g over 3 rho. And let's recall that h, remember, is 1/2t in the radiation era. Right, we're definitely in the radiation era. Okay, we derived that h was 1/2t. So this I can write as 8 pi g for 3, and rho is this pi squared over 30 g star, and then t to the 4. So I get a t squared left over. And then it's useful to think of the g star as a function of temperature. As you can see, it's literally this function of temperature. It's not determined by anything else. It's thermodynamics in some box. It doesn't really care that the universe is expanding per se, although that's the reason t is changing, but it's just a function of t. So let's be explicit about that here. I'll put g star of t. It's that function. Okay, so then you could just easily solve for t. Yeah. That's right. We're in the radiation era.
I saw T squared and like we're in the radiation era, but then I saw it. We're writing it as a function of like.
Yeah, I'm saying.
It, not
I'm saying H equals 1 over T2 in a radiation era. Yeah. All right, so if I solve for T then, I mean time. Okay, that's very simple. So time is proportional to 1 over temperature squared, modulo some little wiggles from the G star. And to sort of put in the numbers and make it sort of a little clearer as to how we can connect T to time. So if I just evaluate G Newton and so on, I can write this as 0.75 seconds. And my G star, I'm going to normalize it to, I don't know, 10, just for convenience. Because, for example, around here, it's around about 10, but that's just the way I'm writing it. And then I'm going to normalize temperature to MeV. Okay, so this is one way you can express that. Okay, so that's the conversion between time and temperature. Right? And so, yeah, so you see down here at an MeV, roughly when E plus E minus is annihilating, that's 1. G star is, well, 10 or close to 10, a little less. And there's a 0.75 seconds. Okay, so order of magnitude, this down here is like a second. And then if we go up to, say, the GeV, well, G star changes a little bit, but the biggest impact is that you put, you know, an extra factor of 1,000 here for temperature, and you square it. So that's why I say you get something like a microsecond. If I'm slightly more precise, GeV turns out to be 0.3 microseconds. Okay, and if I go back to 100 GeV, right, that's basically an extra factor of 100 squared. So now you're down to like 10 to the minus 10 seconds. There's a 0.2 if you do it a little more accurately. Okay, so those are the eras. 10 to the minus 10 seconds, this is sort of roughly electroweak phase transition. This is QCD phase transition. Okay, 10 to the minus 10 seconds, microsecond, and then 1 second is when electron positrons disappear. All right, any questions about that? Okay, so let's have I would like to understand this little transition here in some detail, okay? Because once this has happened, we have a universe after a second that is just photons and neutrinos, and they're going to persist, and they're just going to dominate all the way up to 50,000 years, okay? So I'd like to know what is the energy density of those photons and neutrinos with some precision, okay? And if I just do the simple counting that's on the board, I could just delete the 4 from E plus E minus, and this formula turns out to be slightly wrong. And it's actually useful it's important to get the answer correct, or you make like 10, 20% level errors for the first 50,000 years. So let's fix that. Okay, so what we're going to see is that these neutrinos are a little bit subtle. Is there a question? The estimate will be too high. Yeah, the real answer is it has a slightly less G star. But I want to compute it for you. Okay. So the question now is, what is happening below an MeV? Okay, so just a reminder, yeah, temperature bigger than an MeV, G star we just said is like 10.75. Okay. I don't mean much bigger than MeV, electron mass, when you're up beyond heavier particles, just a little bit bigger than ME, get my point? And then the question is, for T less than ME, what is G star? All right. So this is a little tricky. Right, and remember, ME is like half a mega electron volt, so that's why I'm associating it with MeV. Okay. The naive answer is that G star is 2 plus 7/8 times 2 times 3. Photon neutrinos, E plus E minus, have disappeared. But this turns out to be wrong. All right, let me tell you why it's wrong. So the punchline, which we can explain, is that neutrinos decouple just above, it's very close actually, it's on the margin, but just above an MeV, or just above electron mass, which is 0.5 MeV. So they decouple at about 1 MeV. It's very close, but it's just above. Okay. So what does this decoupling mean? So that is to say, below this MeV, neutrinos are not actually in thermal equilibrium with the photons or the electrons. So there are processes keeping E plus, E minus photons, neutrinos in equilibrium. And so some important processes are like this. Here's E plus, E minus into 2 photons. You can call that process 1. Very rapid process as long as there are lots of electrons around, which is true above half an MeV. And then we can also keep neutrinos in equilibrium through exchange of W bosons. So here's, say, nu bar E plus electron neutrino. Okay. So yeah, photons and electrons are in thermal equilibrium because of this. If this rate is fast enough, but this rate happens super fast because the electromagnetic interaction is kind of big. And then these kind of processes, neutrinos can be in equilibrium with electrons and positrons through these kind of processes. But this rate is not guaranteed to be big because the weak interaction is weak. So we have to be careful. That process may not be very effective at keeping these neutrinos in equilibrium. Right? So you can imagine the photons have some number density, which is order T cubed. It likes to share that with E plus E minus, which likes to share that with neutrinos. And so they all maintain their number densities that are order T cubed when everything's relativistic. Does that make sense? But if this process is very inefficient, then that's not going to happen anymore. And the neutrinos will stop talking to the rest of the particles. All right, so we're going to do some little estimates here. So these are the rates at which these interactions take place. So you may know a rate of 2-to-2 rate is set by the number density of the species involved times the cross-section for that process. And V is the relative velocity. When everything's relativistic, that V is just 1. So we don't have to pay too much attention to it. So let's begin our thinking for T above an ME. So everything's relativistic. Okay? I'm going to start above the electron mass. All right. Yeah, so this is number density. Cross-section. Okay. So these number densities, remember, when everything's relativistic, N is just T cubed, order T cubed. Right? So that's super easy to estimate. And then V is 1 because everything's relativistic. So sigma is the only thing we have to be a little careful about. Well, we have to do some thinking as to what is the scattering cross-section. Right? Either we can spend 5 lectures and try to figure it out, or we can just estimate it, order of magnitude estimate on the board, which is what we're going to do here. So the point is these rates need to be fast in order to maintain equilibrium. That's why I want to compute them. Okay, so let's start with process number 1. This one will be fine. Annihilation rate E plus E minus into 2 photons or vice versa. Let's estimate that. So you're going to see a lot of twiddles here. We're not going to worry about 2s and pi's and 3/4 and things like that for this little discussion. All right, the number density is order T cubed. That was easy. All right, now we have to think about the cross section. So you got to think about this process. So basically, you need to, if you're doing it properly, you'd write down the scattering amplitude, square it, and then you have to do an integral over phase space, and that gives you the scattering cross section. So let's see if we can estimate that without doing all that. Okay, so somehow here at this vertex, there's like the charge of the electron. So the amplitude goes like E squared. So the amplitude, let's say, is proportional to E squared. So let's write that as alpha, is the fine structure constant. There's 1 over 137. And so the amplitude just goes like alpha, and therefore the cross section goes like alpha squared. So that seemed pretty easy. And then you're supposed to do some integral over phase space, and we're too lazy to do that. So this is where dimensional analysis will nail it for us immediately, because I know the rate has units of 1 over time, which is the same as energy, which is the same as temperature. So that thing has to have units of temperature, T to the 1, right? So whatever the phase space gives you, everything's relativistic here. So there are particles coming in, they have their energy. Their energy is order T. Right? The typical spectrum, everything's order T. T for temperature. So whatever that phase space gives you, it has to make this dimensionally correct. So without even doing it, I know it's going to give me a T squared. So that the units are right, and this is alpha squared T. So if you're really hardcore, you could just say, well, there's an alpha squared, and then I just put in a T. You could even short step that argument even more. But you can check that this has, for example, this clearly has units of cross section, right? Cross section is an area, which is 1 over energy squared as well. Right, so that's how you might estimate the rate for this process. And now I want to estimate the rate for this process that involves the W bosons. So we're going to write, again, T cubed. That's from the number density. Here, we've got to be a little more careful. And this one came from the cross section. All right, so now again, there's some factor here. This is like, I don't know, G2 or something, G weak, I suppose. That's the analog of E. Okay, so we're going to get 2 factors of these G's. The G squared, that's like alpha W, and that's the amp. So we're going to write alpha W. Again, same story, matrix element would be proportional to GW squared, which is like alpha W, I'll call it. But I cannot be that lazy at this point, because this W has a mass. And it tries to, if your temperature is just a bit above the electron mass, the W is a very heavy particle, so it tries to suppress this process, right? So this propagator here, if you like, has a factor of 1 over mW squared. That matters. I cannot just ignore that. So the matrix element has a 1 over mW squared. We better put that in. mW squared. Okay, so that's my estimate, proportional to this. And then the kinematics of the external particles sets the rest, and they're all order T. Energy is order T. So I can write alpha W squared, square the matrix element, mw to the 4. And then again, factors of t from phase space, which I just set so that the units work. So this time it happens to be a t squared upstairs. And so this is alpha W squared, mw to the 4, t to the 5. Yeah. You see the temperature dependence is very different. T to the 5 versus t to the 1. And this thing you may know, alpha W over mw squared is the Fermi scale. So that's another way of writing this. This is just G Fermi squared, t to the 5. So that's our estimate for A2. I should put a twiddle here. Unbelievably, these estimates are quite accurate. The prefactor is close to 1. We get a little lucky. Okay, so those are my two estimates. And right, let me mention G Fermi here, which is just related to alpha over mw. G Fermi is like 10 to the minus 5 GV squared. Small because the W is heavy. All right, so let's see. I want to compare to Hubble. These are our rates. Yeah, and then let's compare to Hubble. Okay. So maybe we can come back to this later in the course. But what I want to say for now, without going through a big, long derivation of Boltzmann equation, is that you want these rates to be large to maintain equilibrium. And you should say, well, large compared to what? Well, the figure of merit is actually Hubble. You want the rates to be bigger than Hubble. So you imagine that if these rates that I wrote as capital gamma are much bigger than Hubble, then these processes are happening, and they're not really paying too much attention to the fact that the universe is expanding. The Hubble is kind of small. They happen on some very short time scale, and the universe is just slowly expanding. So that's almost like they were just sitting in a box, and they were just interacting. Okay, it will maintain thermal equilibrium. But on the other hand, if your box is expanding very fast, so Hubble is very big, it's so big that H is bigger than gamma, the two particles here, say the two photons or the two neutrinos, will struggle to ever find one another. The time scale it takes for them to find, which is 1 over gamma, if that's longer than the time it takes for the universe to double, they don't find each other. Does that make sense? So we want to compare to Hubble H. Again, the Boltzmann equation makes all these statements very precise. But the punchline of that is that when a rate is much bigger than Hubble, you maintain equilibrium. And when the rates are much less than Hubble, you drop out of equilibrium. And if that happens to a particular species, like the neutrino, then we say that it's decoupled. Okay. And the crossover, yeah, is gamma pretty close to H, within a factor of 2. All right, so let's just finish off that thinking. So let's compute H then. H is root 8 pi G over 3 G star T squared. And again, I just want to give you an estimate. So let's note, I'm going to define the Planck mass as 1 over root 8 pi G. It has units of mass if H bar and C is equal to 1. And this is about 2 times 10 to the 18 GeV. Okay, that's often considered the scale of quantum gravity. We're not doing quantum gravity per se, but this is a relevant mass scale that's appearing in our Friedmann equation. And in this era here, the G stars are like order 10, okay, or order 3 or so, well, they're about 10 actually, because we only have these degrees of freedom. So this is not a particularly big correction factor here. And so, okay, there's a 10 divided by 3, there's a 3 there, and you take a square root, so there's like a 1.7, so we can be a bit loose with the 1.7, does that make sense? And I'm just going to track the 8 pi g, which is given in terms of m Planck, and the t. So up to a 1.7, this is like temperature squared over m Planck. So that's a neat little estimate for the Hubble. Okay, so now let's just plot all these things. Okay. So this is versus temperature, inverse temperature. Hubble is dropping like t squared. Okay. This thing drops only like t to the power 1. So this drops very slowly. So this goes like this, let's say. This is gamma 1. And so that means, except for maybe the very earliest moments of the universe, you can check the timescale at which the crossing happens, which turns out to be super early. This is a super early crossing. This rate is much, much, much bigger than Hubble, right? Electromagnetic interaction is big. So this rate happens super fast. So that's way up there. And this one has a Planck mass in the denominator. This one's small. Hubble universe doesn't expand that fast. But gamma 2 is the problem. Gamma 2 has this t to the 5. So as the universe expands, this thing is dropping super fast. Okay. So it might be bigger up here somewhere. Draw some curve maybe like this. It's a bit rough. Something like that. Okay, so down here in this era, this process is happening too slowly, and neutrinos decouple. So they stop talking to the rest of the universe. Does that make sense? So they're just left on their own, free streaming neutrinos, and they never meet, and they never annihilate back into E plus E minus, or even talk to photons. And then you just have to compute that point at which that occurs. So let's call this 1 over T d for decouple. Yeah. So you set gamma 2 to equal h. That's when the decoupling occurs. You set G Fermi T decouple to the 5, T decouple squared over m Planck. Right? That's our formula for gamma, that's our formula for Hubble. And so then you easily solve for the temperature of decoupling from this little equation, this number here. And we can just write that down and then finish. One over G Fermi squared m Planck to the 1/3. Okay, so we know m Planck, it's 10 to the 18 GeV, and we know G Fermi, it's 10 to the minus 5 inverse GeV squared. So you put this in, and lo and behold, it's rather close to 1 MeV. Yeah, so neutrinos are, in our picture that we drew so far, the neutrinos were in equilibrium all the way down. And then just below an MeV, they actually stop talking to everything else. Okay, so we'll pick up the consequences for that next time. All right.